Welcome back to Daily Dose of Space. Every time we look into the night sky, we are looking into the past. Light takes time to travel, and even the closest stars appear to us as they were years ago, not as they are right now. But there is a limit, a boundary beyond which we cannot see objects, stars, or galaxies anymore. Beyond that point, the universe becomes opaque, not because there is nothing there, but because light itself could not yet travel freely. Today, we are talking about the oldest light we can still observe. Light that has been traveling through space for almost the entire history of the universe. This is the story of how far our vision really reaches and what that ancient glow tells us about the moment everything began. How far back can we really see? The universe is about 13.8 billion years old. In theory, that means light has had 13.8 billion years to reach us. But reality is more complicated. The universe has been expanding since the Big Bang. Space itself stretches, carrying light along with it. Because of this expansion, some light has traveled much farther than 13.8 billion light years to reach us. Still, there is a fundamental limit. At some point in the past, the universe was so hot and dense that light could not move freely. Photons were constantly colliding with charged particles, bouncing around like light trapped inside a fog. During this era, the universe was effectively opaque. No matter how powerful a telescope we build, we cannot see beyond that wall. And that wall is defined by the oldest light we can observe. The universe before light could travel. In the first few 100,000 years after the Big Bang, the universe was nothing like it is today. It was filled with a hot plasma of electrons, protons, and photons. Temperatures were so high that atoms could not form. Every attempt by an electron to bind to a proton was immediately undone by energetic radiation. Light existed, but it was trapped. Photons scattered endlessly, unable to travel any meaningful distance. The universe glowed, but there was no transparency, no clear path for light to escape. This state lasted for roughly 380,000 years. Then, something fundamental changed. As the universe expanded, it cooled. Eventually, temperatures dropped low enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons had nothing left to scatter off. For the first time, light was free. The cosmic microwave background. That first freely traveling light is still with us today. It is called the cosmic microwave background, or CMB. When it was released, this light was extremely hot and energetic, filling the universe with a bright glow. Over billions of years of expansion, that light stretched, cooled, and shifted into the microwave range. Today, it appears as a faint, nearly uniform glow coming from every direction in the sky. It is the oldest light we can possibly observe. Every photon in the CMB has been traveling through space for nearly the entire lifetime of the universe, carrying information from an era before stars, galaxies, or planets existed. When we observe the CMB, we are not seeing objects. We are seeing a moment in time. Why this light is not perfectly smooth. At first glance, the cosmic microwave background looks almost perfectly uniform. Its temperature is nearly the same in all directions, about 2.7 Kelvin. But tiny variations exist. These differences are incredibly small, on the order of 1 part in 100,000. Yet, they are among the most important signals in all of cosmology. Those slight temperature fluctuations represent regions of slightly higher and lower density in the early universe. Over billions of years, gravity amplified these differences. Every galaxy, every cluster, every cosmic structure we see today grew from those microscopic irregularities frozen into the oldest light in existence. In other words, the cosmic microwave background is not just a relic, it is a blueprint. What we learn from ancient light. By studying the CMB in detail, scientists can measure the age of the universe, its geometry, and its overall composition. It tells us how much normal matter exists, how much dark matter dominates cosmic structure, and how dark energy is driving expansion. It even allows us to test theories about inflation, a brief period of extremely rapid expansion that may have occurred fractions of a second after the Big Bang. All of this information is encoded in light that left its source long before the first star ever ignited. That is what makes it extraordinary. We are not inferring the early universe indirectly. We are observing it directly. The edge of what we can ever see. The cosmic microwave background represents a hard observational limit. Beyond it lies the so-called cosmic dark ages, a time before stars, before galaxies, and before transparent space. We know that era existed, but we cannot see it with light. No telescope, no matter how advanced, can directly observe earlier electromagnetic signals. The universe itself prevents it. Unless we find a completely new messenger. Gravitational waves, neutrinos, or unknown forms of radiation may one day allow us to probe deeper, closer to the very beginning. But for now, the oldest light remains the ultimate horizon of vision. The oldest light we can see is not coming from a star or a galaxy. It comes from a universe that had no structure, no planets, and no life. A universe only just beginning to become transparent. And beyond that ancient glow lies a time we understand only through theory, not observation. The question is not how far we can see, but whether the universe has left behind any other signals from before light itself was free to travel.